All right, let's go through the Chapter 6 test review. Before I get into the weeds, just remember that this is version A, and tomorrow on the test, you're going to be taking version B. So there are many, many similarities. You do need to complete this in one class period, so make sure you know your stuff. Okay, so number one, it gives you a distribution based on probabilities, and it's a pretty straightforward question. It's asking you the probability that at least there's at least two personal computers. So that's, just make sure you know at least includes two. So you just have to add up these four numbers, and that'll be 39%. It's always could be worded like no more than two or things like that. So just be very careful if you know two is included or not. The next one is more abstract because it doesn't give you probabilities right here. It gives you Ks. What you do know though is if you added all of these up, like I have right here, you get 20K. So that's the table total. So like, I didn't write it, but 20K equals 1.0, right? Just like this table up here, if I added all these up, I'd get 1.0. So you could divide by 20 right here to get the value of K. And 1 divided by 20 is 0.05. So that's another way to go about it. I guess then you know when you're doing this question, probability that X is less than 2. Well, again, that does not count 2. Less than 2 does not include 2. So it's just 1 or 0. So that's 2K and 3K is 5Ks. Well, and now you know that K is 0.05. So you could just do, let me show you some of the work here. So 1 divided by 20, that's where K comes from. And then there's 5Ks, so 0.25. I kind of showed it a little bit different here. I did that 5K is what we have out of the table total of 20K. And so that reduces to a fourth because the K's cancel. That's another way to think about it. Number 3 is really, it's a big word problem that's essentially describing a table. And I showed my work down here for it. And I had this thought afterwards, as you went through, you could just create the table. Because first it says $10,000 happens 3/20ths of the time. So this is right here, $10,000, 3/20ths. So that's your first outcome. And then the next outcome is 5,000. And the probability of that was 9 out of 20. And keep going. There's only 4. There's 2 more. And then we have $0 happens 5/20ths. And the last one, be careful, you lose 5,000, so make sure it's negative, and that happens 3/20ths of the time. Now, what are we asked to do? Expected profit is average, so that's when you take 10,000 times 3/20ths, multiply that, then the next one, multiply those, and add them all up. And that's what I've got written up here. I just make sure that 5,000 is negative. This is on the College Board sheet, this process. It is there. It is where you're going to be the whole time is right here in this box on the College Board sheet. But this is what we just did. We did the expected value, E of X. And we took each X value and multiplied it by the probability of it. And then the E, this sigma thing, is you add them all up. So you're going to be spending all the test right here in these boxes. Oops. All right, number 4 is just getting at the formula. So this is confusing, right? This 10(3) in a parenthesis, 10(3) is 10C3, okay? So it has to be A, B, or E because we have 10 rows. So you could cross off these because these would be 8C3. Okay, and it's not that. Excuse me. All right, and it's on the College Board sheet. So that's their notation. I'll show you in a second. Then the next piece is this. This is the probability of getting what we want. Sometimes when I read this, I'm like, what do we want? We are trying to get exactly 3 sevens. So I want sevens. So what is the probability of getting a 7? Well, what are we rolling? We're rolling an 8-sided dice. So on that dice, I'm assuming there's the numbers 1, 2, 3, 4, 5, 6, 7, and 8. So the probability of a 7 is 1 out of 8. And you get 3 sevens. So it's this one right here, 3 sevens. And then this piece is because of the 10 rolls, 7 of them were not sevens. So that's B. Now on the College Board sheet, it is right here. And this, that is like your NCR. Okay? And then this is the probability of success, and this is the probability of failure. All right, next page. I talked about this one in class. This is something you just kind of got to memorize. If you're combining two variables, okay, it doesn't matter if you are adding or subtracting them, you always, 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 always add the variances. You never just add the standard deviations or subtract them. Your path is always through the variances, okay? What's wrong with E is that this would be the standard deviation, sigma, because it's been square rooted. When you square root it, it brings it back to standard deviation. But it said variance, so that's a problem. Okay. Number 6. It has a random variable x, and it is the profit made at a store. It is normal, so there's a big hint. We're not doing binomial. We're not doing geometric. So forget those buttons. It's normal, and it tells you the average and the standard deviation. What's the probability that X is above $400? They make more than $400. So I drew a normal curve, and I have 2 different ways to do this. You could do it with the raw data, or you can do it with z-scores. With the raw data, you put the average in the middle, and then they want to get $400 or more, so I shaded it in. With z-scores, you put 0 in the middle, and you have to get the z-score of 0.8. Now, I did that like this. I took $400 minus the average divided by 50, because that's the standard deviation, giving me 0.8. Now, on the calculator, this is the normal CDF button. You could do it this way, or I'll throw it under here. Well, doing it this way, you guys, would be using the top row. And I think I might have written that wrong as I'm looking at it. I'm gonna have to fix that. Let me fix that. Normal CDF. I want to put the lower boundary as 400, and I had that wrong. So 400, and then up to what upper boundary? Well, I put big number. Just put something so large it covers all possibilities. So put like 20,000, 30. It doesn't really matter. Just put something massive. I'll put 20 grand. A number so far out there, there's no data when you get out to that point. And then you put the average, and then you put the standard deviation, which is 50. That would work. I do know I have the right answer, but I think I typed it in wrong. Another way to do it would be normal CDF again, but now use this information, the z-score row. So now your lower boundary is 0.8. Your upper boundary, I put 99. There's no there's no data 99 standard deviations away from the mean. And then I don't think you have to put the 0 and the 1, maybe you do, but on this row, the average or the mean is 0, and the standard deviation is 1. So this and this will both spit out the same answer on the calculator. You might have a slightly different version than mine. Might be even a little bit better. So I'll do CDF. I just have to type them all in. So if I did the z-score one first, there's the z-score one. If I do it with the actual raw data, that's the one where I did 400 to some big number like 20,000. The average is 360 and the standard deviation is 50. And you can see they're identical. Okay. 7. The card dealer is dealing out 40 cards from a deck. And this is just really getting at bins and bits and that kind of thing. The answer C is better than A and B. And why is it better? Because it says very clearly, after you draw a card, it is replaced in the deck and it is shuffled really well. This guarantees the trials are independent and the probability is the same for each trial. It does not say that on A and B. It does not say anything about replacing it. Here it says shuffling, but it doesn't matter if you take out 40 cards and don't put them back, that means the events are not independent. Especially because 40 is way over 10% of 52. It's not geometric because we have a set number of observations, so it's not geometric. Number 8, I'll show you the College Board formula. You have to determine first off that this is binomial. Why is this binomial and not geometric? It says you are taking a random sample of 10 kids. So this is n. N is 10. Your sample size is set. It does not change. Your probability is also set. 20% of students experienced it, okay? So then, how did I get these two formulas? You don't have to memorize them. Look on your College Board sheet for the binomial formulas. They are binomial here for your average and here for your standard deviation. And these are the ones I used. And I already wrote down what n is and what p is. So you have all the ingredients. You just got to use them carefully. Okay? And plug them in carefully. Number 9, which is true. Sometimes it's helpful to talk about what's wrong with each one. A says binomial requires only 2 possible outcomes for each trial. That's true. However, does geometric allow more than 2 outcomes? No. Both of these have only 2 outcomes, so it's not A. B is a problem because it says the variable can take on integers from 0 to n, but it's not possible for geometric. Remember, geometric means you do something until you succeed. Can you succeed on the 0 try without even trying? That's not possible. So it's not B. E. If x is a geometric random variable and the probability of success is 0.85, it'll be skewed left because of the number being closer to 1. That's not true. Just geometric distributions are always skewed right. Now, like if p was 0.20, it would probably be much more exaggerated like this. Whereas if it was 0.85, it wouldn't be as bad, but it is still going to be skewed. Okay, both are skewed right. So it's not E. D is the one it is, and it just says it's spot on. A binomial, the difference between is that a fixed number of trials in binomial, check, and the number of trials varies in geometric, check. So it's that one. And then here it says binomial is always skewed right. No, geometric is always skewed right. Okay, that's all your multiple choice, folks. Free response. Here gives you a table of data. So this should be a dead giveaway right away, by the way, folks. This is not binomial, not geometric. okay? This is a probability distribution for this variable. Find and interpret the mean. This is when you do 1 times 0.5 plus 2 times 0.3 times blah, 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 blah. And wrote it all out. Just be very careful. There's no button that does this for you. Remember to interpret, okay? Same thing here. This is nasty. This formula is on the College Board sheet. Let me explain it first. You take each outcome and you subtract it from the average, okay? Then you square it. You do this for every single one. Then you multiply by 0.5. But where did 0.5 come from? Right there. So you're going to do that for all 4 of these. 1, 2, 3, 4. Be very careful typing it in because you don't want to make a mistake. Here it is on the formula sheet if you want to see. It's remember, it's not binomial and geometric. It's this. So it's this. And this is what I just went through. This is you take each outcome minus the average, square it, and then you multiply by the probability of that outcome. Remember, sigma means you do this over and over and add them all up. So you did it for all 4, and then don't forget to square root when you're all done, folks. Okay? There is a way you could do this with lists on your calculator. If you put this in your calculator, on the lists, on the first one you did 1, 2, 3, oops, 1, 2, 3, 4, and then, what is it, 0.5, 0.3, 0.1, 0.1. Then when I do stat calculate number 1, let me go back so you can see that. You see what number 1 says there? It says X list name, comma, frequency list. X list name, comma, frequency list. So, oops, calc 1. The X list is list 1, and I want to do that based on the frequencies or the probabilities in list 2, right? So this is L1, this is L2. And then when I do that, it spits them all out. And there you see sigma, 0.979, and I got 0.98, and I rounded it. So it can do it for you if you're worried about not getting the buttons pressed right. And interpret. Last one, this is a throwback here as well. It's still connected to Part B and Part A and all this. We are transforming the profit. We're multiplying it by 0.75 and subtracting 0.05, okay? They get 75 cents per DVD, and they pay 5 cents of fixed costs. So we're like transforming the data. This goes a ways back. If we are transforming averages, they are affected by the entire equation. So we have the 0.75 and the 0.05. We use both of them, and we just throw in the average, 1.8 right there. To figure out, on average, they would profit $1.30 for every DVD. Sorry, on average per customer, they would profit $1.30. Okay. If we want to find the standard deviation for the profit, standard deviation is not affected by subtracting the 5 cents. So notice I only did the 0.75, and I took my answer for standard deviation and threw it in there. Okay. So that's the key takeaway for the whole year. Remember, standard deviation is only affected by multiplication. It is not affected by subtraction or addition. All right, 11. This one says ACT scores have an average of 20.9 across the country, and this standard deviation. So if any kid takes it, on average, they will get 20.9. Okay, that's what we would expect them to get. A random student from across the country. Now, what if we took 2 students randomly and we subtracted their scores? Well, we would expect them, on average, to each score the same, right? So on average, they would have the same scores, so what would their difference be? 0, okay? Seems a little bit strange, okay? If you two random kids, you would expect them to score the same amounts. Now, what's the standard deviation of the differences? Oh, this goes back to question 5. You're like, okay, I'm subtracting standard deviations, okay? But remember, how do we do that? No matter what you add the variances, okay? Always, always, always add them. So they both have the same standard deviation, right? Each kid, 4.8, 4.8. You have to square them because when you square them, that makes it a variance, okay? And then square root it when you're done. Two combined standard deviations, always add the variances, okay? And then square root it back to make it back into a standard deviation. C, we're going to use a normal model. Why are we using a normal model? This is not binomial. It's not like pick 5 kids and what's a success? We don't even know what a success is. It's not keep going until you find a kid who fill in the blank. It's not binomial. It's not geometric. So it's a normal model. We have the average. We have the standard deviation. So we can use that to get a z-score for what they want. The question is, what's the probability their difference, so we just did differences, right, is greater than 6. Okay, so here I have the raw data. Their average difference is 0, 6 or greater, okay, and here I did it with z-scores. Your z-score average is 0 in the middle. The z-score for 6 is 0.88. And then I would do the normal CDF button. What I've shown here would be using the bottom row, the z-score row. And you get about 19%. For my upper boundary, I just put 99. Lower boundaries, the z-score of 0.88, upper boundary 99. Okay, 12. The soccer player is going to take kicks. It tells us each kick's independent, voila. You're going to keep kicking until you fail to score a goal on your penalty kick. It says, what's the probability he fails to score? The first time he fails is his 5th kick. So he makes 84%, so he misses 16% of the time, right? 84 plus 16 is 100. So here is the probability that that this happens on the 5th try. So he had to make 4 shots, right? 84% of the time, 4 times in a row. Then on the last try, he missed. You could do the Geo button on this, Geo PDF button. Yeah, PDFF. Your chance, this is a little counterintuitive, but this is how you put it. The counterintuitive part is this, 16%. Because usually we say, you keep going till you succeed. In this case, succeeding, or when he's done, this player, or she's done, they're done when they miss. So the probability that you put here is 16%. Okay? That's what I put right there. The next one, probability he scores on 5 or fewer of the next 10. So this shifted gears on you, right? This one said the first time you fail, so it's geometric. This one says, no, back up. They took 10 kicks and they made 5 or fewer. It has now switched to binomial. So be careful, right? There are 10 trials. Scoring is 84% of the time. So you have N and you have P. 5 or fewer, you could put a 5 here using the CDF button. I want you to write out at least 2 pieces of the puzzle like we have in the past. 10C5, make 5, miss 5. So this is the probability of making 5. This is the probability of making 4, right? 10C4, he made 4 and missed 6. Okay, so there you go. That only happens about 1% of the time. Then it says the player was out of action with an injury for several weeks. When the player came back, he scored only 5 times. He did this, in other words. Is it evidence that his success rate is actually lower than 84%. So this is all found upon the assumption that he is an 84% shooter. And if he is an 84% shooter, this only happens 1% of the time, which makes me kind of think, well, maybe with being away on injury for so long, that his success rate did decline, right? If his probability of success is still 84%, then we would expect a result like this only 1% of the time. That leads me to believe his success rate did go down when he was hurt. Oh, hey, look at that, we're done.